So we're getting into chapter 3 of calculus now, which is talking about more of using the derivative. So I always felt like this was pretty basic. If you already understood what the derivative was, all of this stuff makes a lot of sense. So I think this is also just a good practice chapter of the derivative. So what are they asking here? Example 1, find the value of the derivative at each relative extremum. So I guess vocab, relative extremum, what does that mean? Just relative maximum, relative minimum. If those words don't sound familiar, well, they actually tell you right here. Here's your relative maximum. See, it's just like on that part of the graph, it's just the highest. Like maybe it comes up here later, but we don't care. It's a relative maximum, just means it has a little peak there. And so what's the derivative at that point? Well, if we sketch the tangent line, we see that that tangent line has a slope of 0, and the derivative is just the slope of the tangent line. So the derivative there is 0. And that makes sense too. That's kind of what this whole thing is getting at, is that if your graph goes up and then goes down, well, that's going to be a relative maximum. And just based on that sketch, you can kind of tell if it turns around, at some point it's going to have to be flat, right? I'd say so. So that's a relative maximum. It's got a derivative of 0. But here's another thing that can happen. So see how this point is definitely a relative minimum. It's at the bottom there. But what is its derivative? So as we talked about before, anytime there's a sharp corner, the derivative is undefined, because the idea is, what is a tangent line? A tangent line is a line you can draw that just goes through one point in the graph. And you see there, you can only do one of them. You adjust that at all, it would go through 2 points. But here, you can draw a bunch of lines that just go through that bottom point. So there is no way to write a tangent line there. The derivative does not exist. But that's still a relative minimum. So what they're showing us here is that there's like kind of 2 possible ways there can be relative minimums. If the derivative is equal to 0, and if the derivative does not exist. And you see in this example, here's another one where the derivative is equal to 0. At the peak and the valleys of those sine curves, it flattens out, and that tells us it's going to have a relative minimum. So here it's also showing us, of course, those are like English words, so if you know English, you should be good with that. Minimum is the bottom, maximum is the top. So relative maximum is where there's a peak, where there's a hill, relative minimum, where there's a valley. And this is the key takeaway, that when we're doing these are the 2 options we're looking for. We're looking for the derivative to be 0 and the derivative to not exist. If that happens, it's possible that we might have a relative minimum or a relative maximum there. Of course, I said that swapped, but you get it. So here's an actual problem that we're going to do. We want to find the extrema, maybe relative, maybe absolute, of this function on that interval. So they are talking about the absolute in reality. They want to know the absolute highest this function goes and the absolute lowest this function goes. So what are we going to do? Well, we're going to use the fact of what we just learned, is that whenever the derivative is equal to 0 or undefined, that's when there might be a turnaround point. But we've also got these to worry about. So here's the thing. Maybe the graph looks like this, where it like stops here. Like that's our, I could even sketch it out here. Like this is our -1 and this is our 2. And so like maybe we'll set it equal to 0 and we'll find those points where the derivative is equal to 0. But if they're talking about the absolute highest and absolute lowest this function goes, then what we care about is those points actually. So what we're going to do is we're going to find all the places we care about. So the numbers where this happens, there is a vocab word for that. We call those the critical numbers. And all that means is just the potential places for minimums or maximums. So what we're going to do here is we're going to find the derivative, see when it's 0, see when it's undefined, solve for x for when that happens, and then we'll get all the numbers that we need to look at. So let's do it. So here's our function. Let's take the derivative. So that's pretty quick and easy power rule for the derivative. So we're going to bring the 4 to the front and multiply it and decrease the power by 1. Bring the 3 to the front and multiply it and decrease the power by 1. So there's our derivative. Now what do we want? We want, when is that derivative? 0. And when is it undefined? So first off, when is it undefined? Well, it's never undefined. Polynomials are never undefined. So you could say D and E does not exist when it's undefined, which is fine. That'll happen plenty often. But then what do we want? We want when the derivative is equal to 0. So let's see. So now we have an algebra equation we have to solve for. And so that's how it can be difficult if you're not comfortable with it. Now we're trying to solve this algebra equation. So how do you solve this algebra equation? Well, I think you've got to factor is what I would do. I would always say, what's the biggest thing you can factor out of everything? We can factor out a 12x squared. So we're just left with x minus 1 equals 0. And now it's the algebra ideal. We got two things multiplied together to be 0. So one of them has to be 0. X equals 1 and x equals 0. So those are the critical numbers. Our critical numbers here are 1 and 0. So all we're going to do now, because we just care about finding the highest and the lowest point, we're just going to plug in all of these numbers we care about. So don't forget the endpoints. That's critical. People forget about the endpoints a lot because we're so used to and we care so much about finding those numbers. And we do need to plug in those numbers in to see what happens with those numbers. But we got to do the endpoints too. And then at the end of this, we'll look at the graph and we'll see. So now think about what we're doing. This is another thing. You got to make sure your equations are kept straight because we don't want the derivative to be as high as possible. We want the function to be as high as possible. So when we plug these numbers in, we're not going to plug them in to the derivative. We have to plug them into the original function, which will probably be better on the math for us. So let's see. We plug in negative 1. 3, negative 1 to the 4th is just 1. So 3, plain 3. Minus 4 times negative 1 cubed. Well, negative 1 cubed is still negative 1, but then times a negative. And so see, this is more algebra skills coming in, just arithmetic skills. So we get 7 when we plug in negative 1. Okay? 0. You plug in 0, that's pretty easy. 0 to the 4th minus 0 cubed, that's just 0. You plug in 1, that's also pretty easy. 3 minus 4, so negative 1. You plug in 2, oh, that's well more math. But I think you should know powers of 2. 2 to the 4th is 16. 16 times 3, 48. 2 to the 3rd is 8. 4 times 8, 32. So then you get 16. And honestly, that's another thing about calculus is like, I feel like the trend nowadays is to say you don't really need to know your multiplication tables because like there's calculators and stuff. But if you have to whip out a calculator in the middle of all these problems, it sucks. And of course you can still do it, but it's not fun anymore. And the whole point of math is to have fun. So what do we find? Now we're looking for the lowest point and the highest point. So looks like we can say here, there's where we found the lowest point. And here's where we found the highest point. So these are our absolute max. The maximum on this interval is the point x equals 1, y equals negative 1. Or no, that was the minimum. That was the lowest it got. And then the max was 2, 16. And we know it can't do anything other than that because we found all of the possible turnaround points when we set the derivative equal to 0. So let's just look at this graph and let's just confirm what we found. So let's type in the graph 3x to the 4th minus 4x cubed and get it looking better. I hate Desmos has been doing that a lot lately. There. So there we go. So you see the lowest it's at is 1, negative 1. And see, I guess we can only look at it on that interval. So to do that, you go negative 1, x, 2. There we go. So that's just the part of the graph we're looking at. So what's the lowest it gets? That's what we found right there, 1, negative 1. What's the highest it gets? That's right there at 2, 16. It would be defined if we did something like that. 2, 16. And also interesting to notice here, they didn't really ask for it, but notice that at 0, it's actually not a minimum there. but it still does flatten out. And yeah, that is called a point of inflection. I think somebody said in the chat that it flattens out there, but it's still not a minimum. But then it keeps going back up. And in the next section, we'll probably talk about strategies to figure that out. But in this section, we don't really care about it. We're just looking for on the whole interval. So we got to find our critical numbers, and we got to plug in our critical numbers as well as the endpoints of the interval. Don't forget that. That's important. All right, so here's the next problem. Same exact type of thing. So we want to find where the derivative is equal to 0 or the derivative is undefined. So let's do that. Let's find the derivative. That is a great question I just saw pop up in the chat. We'll get to that after this question. So f prime of x, take the derivative. So derivative of 2x is 2. Here, power rule. So 2/3 to the front. So cancel out the 3. Decrease the power by 1. Interesting. So I'd like to fix that a little bit. Because what is a negative exponent? Negative exponent means we're getting fractions involved. So that's 2 over, go ahead and write the cube root of x. So that's our derivative. I still want to mess with a little bit, common denominator. So 2 cube root of x minus 2 over the cube root of x. And so now what? We want to say, when is that derivative 0? And when is that derivative undefined? Well, again, I'll start with undefined, but here it actually is undefined somewhere. Look, when x equals 0, it's going to be undefined because the cube root of 0 is 0. So this derivative is undefined at x equals 0. So that's one of our critical numbers. And then what's the other critical number? When it equals to 0? So notice, I think we said this last time, when it equals to 0, just the top of the fraction really needs to be 0. So then you know that 2 times the cube root of x minus 2 equals 0. So add 2, divide by 2, the cube root of x equals 1. Cube both sides, x equals 1. So 0 is when it's undefined. 1 is when it's equal to 0. So we have to plug in those numbers and negative 3 and 3 because that's on our interval. So let's just do that. We're going to plug it into the original function, not the derivative. So you plug in negative 1, you get negative 2. I guess I'll write it out. So f of negative 1 equals negative 2 minus, I guess that's kind of, I'm going to write that out for now. Negative 1 to the 2/3. Well, that's just squared. That's just always going to come out positive if we plug in 1, because we squared, it's positive 1, and it's the cube root of positive 1, which is 1. So 3 times 1 is 3, so it's just negative 2 minus 3. So that's negative 5 there. Okay. 0. So sometimes when you get a derivative as undefined, a lot of the times you'll also get that the function is undefined. But that's not what happens in this case. You plug in 0, because 0, you can do the cube root of 0, it's just 0. So you plug in 0, you just get 0. F of 1, you plug in 1, it's similar to before, but it's a positive 2. So that's a negative 1. And then f of 3, oh, that's going to be dirty, is going to be 6 minus 3 times 3 to the 2/3, which means 3 squared, the cube root of. So the cube root of 9. That's interesting. I like that. I like some of these textbook problems. Why do I like that? I like that because we can estimate. We don't need a calculator to see which is bigger. So what are we going for? What do we have? Well, our lowest is definitely negative 5. But then what is this? What is the cube root of 8? Or what is the cube root of 9? Yeah, we got to estimate what's the cube root of 9. So the way to estimate that is to say we have the cube root of 9. Well, that's going to be a little bit bigger than the cube root of 8, right? But then definitely smaller than the cube root of 27, which means 2 is less than the cube root of 9, which is less than 3. So that's in between 2 and 3. Definitely a lot closer to 2, though. So Actually, maybe that's tough to see without. So I would say this is about 6. I would say this is just less than 0 when we plug in 3. I would be pretty confident about that. I guess we could whip out a calculator and say, what is 6 minus 9 to the 1/3? Oh, yeah, that's definitely 4. Oh, I forgot to multiply by 3, though. Right, that's why. I forgot to multiply by 3. Yeah, so that's why I figured. Just less than 0. That 3 is supposed to be there, right? Yeah, so just less than 0. So that's the maximum. This is the maximum right here. Just less than... Oh, no. 0 is the maximum on this, then. Wait a minute. I mean, that's the math we found. Let's look at the graph and see if we made a mistake. Let's look at the graph and see if we made a mistake. So if we look at this graph, it should be 2x minus 3x to the 2/3. Oh, we didn't make a mistake. I didn't expect the graph to look like that. I expected the graph to go vertical for a second, but that makes sense that it's not. I expected the graph to look more like this, where it goes vertical for a second. But no, it doesn't. It makes sense. It's squared. That's like absolute value. It just flips around. So no, I think we're exactly right. So where did we want that graph? We wanted that graph from -1 to 3. I think that's also shows one of my favorite parts of math, that like if you do the math right, it's right. So what have we found then? Our absolute maximum there, you see it almost makes it back up. But no, our absolute maximum on this interval at least is 0, 0 for sure. And then the minimum is, yeah, down here at -1, -5. So if the math checks out, it's got to be correct. Beautiful. No mistakes. What is hard, I think it's important to remember, at least I forget a lot, is to do it when it's undefined. That you've got to remember when it's undefined as well. Otherwise, we wouldn't have caught that. All right. So now we're doing the same thing. We just got to do it with trig functions. But it's the exact same deal. So we're going to say, what is the derivative? So the derivative of sine is cosine. And then the derivative of cosine is negative sine. So this will end up being positive sine of 2x. And then because chain rule, you keep the inside the same, but then you multiply by the derivative of the inside. So now we're going to go, what are we going to go? Well, we're going to set that equal. So when is it undefined? It's never undefined. Cosine and sine are never undefined. So we're happy with that. But we got to say, when is that equal to 0? And there's a few interesting things we could do. I would definitely say we should divide everything by 2 first, just to get that out of the way. So then we have cosine of x plus the sine of 2x. And I would jump back to your pre-calc here and think about the double angle formula. We actually just used it to prove that derivative, which y'all missed on YouTube, but you saw if you're on Twitch. So let's do that formula again. Except for here, it's x plus x. So it's sine of x, cosine of x, plus cosine of x, sine of x. And that's how I remember it. If you're better, you would realize, and then I would just say that that is 2 sine of x, cosine of x. So now we have this equals 0. And a lot of the times it's good to factor. So I'm going to factor out a cosine of x, because then what am I left with? 1 plus 2 sine of x equals 0. And now it's the whole deal. You got two things multiplied together to get 0. You set them both equal to 0. So cosine of x equals 0, and 1 plus 2 sine of x equals 0. So we're looking for when sine of x is -1/2. So then we got to know our cosine and our sine values. But notice we're only looking from 0 to 2 pi. So we only got to actually think about it from 0 to 2 pi. So from 0 to 2 pi, when is the cosine equal to 0? Twice, right? At pi over 2 and 3 pi over 2. And when is the sine of x equal to negative 1/2? Well, it's equal to 1/2 at the pi over 6's, but then it's negative. So all students take calculus. So it's in the third and fourth quadrant. Excuse me. So that's 7 pi over 6 and 11 pi over 6. In radians, of course, as always. So now we have our critical values. That's a lot of plugging in to do. That's a whole lot of plugging in to do. Well, when we plug in 0 and 2 pi, we'll get the same thing. But technically here, we're getting 6 different values we got to plug in. And I imagine this is no calculator. It's not that bad because a lot of stuff will just end up being 0. So let's see. We're going to do f prime of 0, which is what? Well, sine of 0 is 0. Cosine of 0 is 1. So this is negative 1. F of pi over 2, let's see, the sine of pi over 2 is 1. So we multiply that by 2, so we get 2. And then we're doing the cosine of 2 times pi over 2. So 2 times pi over 2 is pi. The cosine of pi is negative 1. So minus negative 1 is plus 1. So we get 3. Hope I'm not making little math errors here on my sines and cosines. So let's do f of 3 pi over 2. So what's sine of 3 pi over 2 is negative 1. So this is negative 2. And then the cosine of, let's see, it's times 2. So it's actually the cosine of 3 pi, which is really just the cosine of pi, which is negative 1. Cosine of pi is negative 1. That's true. So minus negative 1, so plus 1. Yeah, just like it was before. Yeah. So then that's negative 1 again. Okay. So then 7 pi over 6. F of 7 pi over 6 is the sine of 7 pi over 6. Well, that's what we said, right? Was negative 1/2. So you multiply that by 2. That's negative 1. And then the cosine of 7 pi over 3, because the 2's cancel. So you take away a 6 pi. That's just the cosine of pi over 3, which is 1/2. So minus 1/2. Negative 1.5. That's the lowest we've got so far. F of 11 pi over 6. So what's different? That's in the same family, but it's in the third versus the fourth quadrant. Except for you can't totally say that because of the sine, because of the cosine of 2x. But so the sine of 11 pi over 6 is negative 1/2. Multiply it by 2. That's negative 1. The cosine, I'm going to have to write that down. The cosine of 11 pi over 3. So I can take away a 2 pi. That's like what I did last time, which is like a 6 pi on the top. So that's the cosine of 5 pi over 3. Yeah. Which is like the pi over 3, but in the fourth quadrant, and it's positive there. So cosine of pi over 3 is 1/2. Oh, right, because that's like what I did last time. But it's positive, but then it's minus, so it is like minus 1/2. So that is also negative 1.5. That's not really surprising, honestly. And then f of 2 pi. 2 pi is literally the same thing as 0. So even when you do the cosine of 0, the cosine of 4 pi, those are the same. So that's also going to be negative 1. So what is the maximum? Should be pi over 2 comma 3. What is the minimum? There should be 2 of them if we didn't make a math mistake. I'm honestly going to be impressed with myself if I make a math mistake. But I'll be even more disappointed with myself if I do make a math mistake. But let's look. Cosine of 2x. Let's go ahead and just so it's super clear, let's put our boundary on from 0 to x to 2 pi. Yeah, I mean, that looks pretty much exactly right. When we said f of pi over 2, it gets to 3. Pi over 2 is 3. 7 pi over 6 is negative 1 half. And 11 pi over 6 is negative 1 half. Always feels real good to get the answer right. It really does. And that's it for that section. And honestly, the rest of this section is just like a lot more of that. I feel like this section got really repetitive when I took calc. It's just all stuff that honestly makes a lot of sense. It's just laying it down and it's just getting you more practice time. Because to learn calc, you gotta practice. You can't just watch me do it. You gotta practice yourself. So tune in next time, probably tomorrow, for Rolle's theorem.